Hello everyone, this video will provide you with a solution manual for the second midterm exam of structural analysis. So let's get started right away. Question 1. In question 1 we are asked for 4 different beam cross-sections to determine the most logical location of the shear center without performing any calculations. This means that we should be able to determine it by simple reasoning. Let's take a closer look at the figures here. For section 1, we notice that all the beam members are crossing each other in point 2. This means that point 2 will be the shear center. In section 2, we notice that it is point symmetric around its centroid. This means that if we are going to load this section with a vertical shear force, the shear flows in the upper and the lower member will counteract each other in a moment. This is the same for if we would apply a horizontal shear force. Therefore, the shear center of this section is point 1. Now for section 3, we notice that it is the same as section 1 with the addition of a small tail. The symmetry axis is still the horizontal axis, so we know that the shear center will be not on point 5. Now, if we would apply a vertical shear force on this section, we know that the shear flow in the little tail will be in the same direction as the shear force that we apply. This means that if we apply a vertical shear force that goes upwards, the shear flow here will also go upwards, therefore creating a clockwise moment around point 2. If we would then look at the external forces acting on the cross-section, due to equivalence, we know that the shear force should also create a clockwise moment around point 2. Therefore, the shear center of this cross-section will be in point 4. Now, section 4 is a C-section on its side, which we all know very well by now. We know that the shear center is for sure on the vertical symmetry axis. And then because in the case of a horizontal shear force, the shear flows in both vertical members will be in an opposite direction, we know that the shear center will be in point 5. Let's go on to question 1b. In this question we are asked for 3 cross-sections. Which of the 3 weld locations will have the highest shear stress? So first of all, let's start by looking at section 1. Section 1 is a T-section where on the top member there's 2 side members. We know that in the open ends the shear stress will be 0. So in this end, this end, this end, and this end, there will be no shear stress. From these points inward, the shear stress will only increase. So along this path, the shear stress will increase, same with this path, and same with these 2 paths. This means that the 2 possible locations for the highest shear stress are location 2 and 3. Now we should notice that for point 2, the path from the point where it's 0 to point 2 is a lot bigger than point 3. This is why point 2 will be the point with the highest shear stress. Then we go on to section 2, which is a C-section on its side. For this section, we know that at point 2, the shear stress will be 0, same with the open ends. Now the 2 possible locations for the highest shear stress are 1 and 3. Now we should notice that 1 is placed horizontally while 3 is placed vertically. So basically the question is, on which side of that corner will the shear stress be maximum? Note that in the vertical members, the increase of the shear flows will be quadratically, while in the horizontal member, the decline will be linear. This means that if we look at the location just beyond the corner, the location that is placed horizontally on the vertical member will have a higher shear stress, since due to the quadratic decline, the shear stress is slightly higher on that side of the corner. So, point 1 has the highest shear stress. For section 3, it's a C-section that's placed. Section 3 is just a regular shear center, And for this section, we know that it's again it's gonna be 0, the shear stress is 0 at the O. Section 3 is a regular C section. In this case, we again know that on the open edges, the shear flow will be 0, and from there on, it will only increase towards the center. In this case, we know that on the vertical member, the shear flow will be a kind of parabola shape. Therefore, point 2 is a point that will have the highest shear stress. So now that we have solved question 1, we will go on to question 2. In question 2, we are asked to consider a beam section which is carrying an internal torque, an internal vertical shear force, and an internal moment. Question 2a then asks us to calculate the internal shear stress that is acting in a cross-section for the internal shear force of 100 kilonewtons and an internal torque of 90 kilonewton meters. Note that the magnitude of the moment is not given in this question, but that's okay since we don't need the moment to calculate the shear stresses anyway. Let's start with outlining the procedure for solving this question. The first step will be superposition. We will use superposition to calculate the shear flows due to the shear force and the torsion separately, and after that we will add them. The second step then is calculating the shear flows due to the vertical shear force. We will do this by starting with calculating the delta Q's over all the booms, which we can then use to calculate the shear flows in the different sections. After this, we will use the torsion to calculate the torsional shear flow, and then we're ready to sum everything up and calculate the shear stress. So let's dive in right away. Superposition. This means that the section with acting the vertical shear force and the torsion can be split up with first considering the shear force and then considering only the torsion. We know that the equation for calculating the shear flow in an idealized structure is this one. Now, let's take a closer look at it, because we can make our lives a lot easier here. We know that there's no Vx acting on the structure and that Ixy is 0 because the structure is fully symmetric. So we can cross out a lot of terms in our equation. What we are then left with is an equation that looks a lot less scary than the one I've written down before. Namely, QB is now minus Vy divided by Ixx times the sum Bry. Because the section is closed and there's no apparent location where the shear flow is 0, we will start with calculating the delta Q's over all the beams. The equation from this can be derived from the previous equation, and it's this one. But let's take a step back first, because I want to clarify something. Because in this figure, it's quite apparent that in a non-idealized structure, the shear flow due to the shear force obviously will be 0 in the locations where the shear force is crossing the y-axis. However, in the idealized structure, there is a boom here, and the shear flow in that boom cannot be considered 0. Therefore, we will need to calculate the delta Qi's over all the booms. Let's start with calculating Ixx. And let's start by filling in the boom areas that are given in the question. Then the y locations, pay attention here because the y-axis is positive downwards, which means that the upper 3 booms have a negative y location. And the lower 3 booms have, of course, 50, not 500, have a positive location. Then I'm gonna go on with calculating the Ixx for all the booms separately. For boom 1, this is 6100, and it's the same for boom 3, 4, and 6. Then for booms 2 and 4, it can be easily calculated that the moment of inertia is a bit bigger. Summing this all up, we can find that the total moment of inertia is 7,720,000. Now I want you to recall that the equation for delta Q was minus Vy divided by Ixx times B times Y. Note that Vy was equal to 100,000. So we can also simply fill in this equation for all the booms. For boom 1, so now that we have all the shear flow jumps for all the booms, we can go on and calculate all the shear flows in the booms. I have drawn the section here, and note that I will define a positive S in a counterclockwise direction. Note that it really doesn't matter that much in which way you define your direction. Just be careful that you remember how you defined it and that you are consistent. To start calculating the shear flows, we can start with the complete upper side, where we know that Q21 will be equal to Q32 plus delta Q2. But also due to the symmetry, we know that Q21 will be the same but opposite side of Q32. From this, we can know that Q21 will be equal to half of delta Q2, which is 171 newtons per millimeters. Okay, now that we know this, we can erase all of it. And we can start with calculating on the shear flows. We remember that Q21 was 171 newtons per millimeters. Therefore, Q16 is Q21 plus, which is 329 newtons per millimeters. So these are all the shear flows in all the sections. We can now perform a final sanity check in the sense that our initial statement that Q21 will be same but opposite sign from Q23 still holds. And if we add delta Q2 to Q32, we get Q21 that we initially calculated. So when we then go on and draw this on the cross section, we see that on the left side all our shear flows are in the direction that we initially defined, but on the right hand side all the calculated shear flows are negative. This means that all the shear flows are in the opposite side, in the opposite direction of the path that I defined. Then one of the final steps is calculating the shear flow due to the torsion. Remember, the equation for this is Q(S0) is equal to T divided by 2AM. Now remember that my definition of the path was counterclockwise positive, but our torsion in this case is clockwise. Therefore, we will use minus 9 times 10 to the power 6 Newton per millimeters. Note that I have converted the kilonewton meters that are given to Newton millimeters. Then the next thing we need is the enclosed area. We can see that our cross section is in fact simply one rectangle and two triangles. The area of the rectangle is 100 times 300, and the area of each triangle is half times 50 times 300. If we sum all this up, we get an area of 45,000 square millimeters. Square, of course. So if we fill this in, that Q(S0) is minus 100 newtons per millimeters. Since this is negative, it is a shear flow in the clockwise direction, which was to be expected since our torsion is also in the clockwise direction. If we then recall our shear flows due to the vertical shear force, we remember that they went like this. Now, since our torsion shear flow is in the clockwise direction, we know that the right-hand side shear flows will be amplified by this extra torsion shear flow, while the left-hand side shear flows won't. We also remember that the Q for 3 was the biggest value with minus 329 newtons per millimeters. So the total torsion in this member is minus 429 newtons per millimeters. Now remember that in order to calculate the shear stress to the shear flow, we have to go back to the original section. In the original section, the thickness of all the walls was given to be 2 millimeters. Therefore, the shear stress in member 4-3 is equal to Q divided by T, which is 941 divided by 2, which comes down to minus 214.5 megapascals. Note that there was no question 2b on the exam, as this was used for extra room for the previous question, so we will go on to question 2c. In question 2c, we are asked to calculate the location and the magnitude of the maximum internal normal stress. Now, we are going to go back and take a look at the initial cross-section. Note that this cross-section is fully symmetric, so we can use the symmetrical bending formula, and that M creates a tension in the positive xy quadrant, therefore we can use it as a positive sign. Remember, the equation for symmetrical bending is sigma is equal to mx times y divided by I. And in this case, as we stated that the moment causes a tension in a positive quadrant, mx is equal to 20 kilonewtons meters, which is of course equals to 20 times 10 to the power 6 Newton millimeters. From the previous question, we remember that I is equal to 7,720,000 millimeters to the power 4. So then, from this we can determine that the maximum normal stress will act at the locations that have the highest distance from the x-axis. Looking back at the original question, this will be either boom 2 or boom 5. So, y will be equal to plus or minus 100 millimeters. Note that I use plus or minus here to include both boom 2 and boom 5. If we then fill in the equation, we get that sigma is 20 times 10 to the power 6 times plus minus 100 divided by 700,720,000. I forgot the units here, so let's fill those in. This is Newton millimeters, these are millimeters, and these are millimeters to the 4th. Working this out, this will come to plus or minus 259 megapascals in boom 2 or 5. So in this case, two locations can be given since boom 2 will have a negative compressive stress and boom 5 will have a positive tensile stress of the same magnitude. Then, for the final question of this exam, we're asked to consider a design iteration where two of the walls have an increased thickness. Note that this is obviously a typo and it should be the top right and the bottom left wall, which is also clearly indicated in the drawing and with the subscripts. Now, based on this change, we have to identify how the previous calculated normal stress will change and how its location will change. Now, let's take a look at the implications of the changes that are made. First of all, IXY is no longer 0, since the cross-section is no longer symmetric, so the bending problem is also no longer a symmetric bending problem. Furthermore, due to the increased areas, we know that IXX will increase and IYY will also increase. Now, let's take a look at the formula for unsymmetric bending. Now, we know that there's still no my acting on the cross-section, so we can remove these terms from the equation. Then if we look at the entire equation, we can see that the denominator will increase because IXX and IYY will both decrease, and this will not be counteracting by the IXY because the IXY is rather small. So sigma will decrease. Then if we take a look at the location, we can see that the neutral axis will no longer be the x-axis, however it will be slightly tilted. But since IXY is smaller than IYY, we know that the y-coordinate will be more important to determine the location of the maximum stress than the x-coordinate. Therefore, boom 2 and 5 will still be the locations of maximal shear stress. Then for a final note, I would like to thank you for watching this video, and I hope it made things a bit more clear.